So thank you everybody for joining in. This is another round of Bitcoin Core peer review club where we usually review PRs, but we decided to change taste today and we are gonna do a BIP review. And as usual with other PR reviews, the process remains the same. The participants are expected to read through the BIP, and here we are going to do technical discussion around the merits and the ideas of the BIP. And there is an open PR on this BIP. It's in draft, so it's work in progress. But this is going to massively impact the Bitcoin P2P network and transaction relay efficiency. So without any further ado, let's get on with it. And Prabhat, the stage is yours. Let's roll.
So hello everyone, I'm Prabhat, and now I'm going to review BIP 330, which is transaction announcement reconciliation. So the main motivation behind this was we are always sending like transactions. The nodes are always sending transactions to the nodes. So if I assume like this is my node here, and I have another node. So what if a node is trying to send a TXID that it has received from, let's say, another node? So it gives us a INV message, and from that INV message, it tells us, it gives us a TXID. With this TXID, the new node which has received the INV message sees that there is a new transaction that I have got. Then it checks that in its mempool if there is this transaction in its mempool, and if it's not, it sends a get data message to the other node, and then the other node sends it the whole transaction. So the problem with this approach is that this approach is very bandwidth inefficient. I guess we have 300 bytes of bandwidth per channel, per node to node channel. So let's say if I am sending like INV messages, 32 bytes of it is TXID, which is a lot considering that I also have to send the transaction data next time. And
right,
let's assume there are a lot of transactions, like there are a lot of transactions being displayed and being shared among the network. So let's say the current algorithm that works in transaction relay is flooding. So what happens in flooding is that whenever a node gets a new transaction ID, a new transaction from the parent node it got, it will not send that data of INV message. What it will do is all the other nodes it is connected with, it will send the other nodes an INV message with the same transaction ID, and then all the nodes will follow the same procedure what I said above. Now this is where the problem starts. A lot of nodes might have received this transaction ID before. Now let's take a scenario where this node is connected with another node, and this node is also connected with this node, and which in turn is connected with this node. So let's say we give our first INV here and another INV here. So this transaction which we sent has reached this node and has reached this node. Now what both of these nodes will do is they will send the INV message to each other, which is a waste because now they will not respond to the transaction because they already have it. So this is the problem currently that is in the Bitcoin protocol. And what is the what is the complexity of it is that there are let's say n channels totally, n nodes. So let's say there are n nodes, and on an average, let's say there are k channels. So k connections with other nodes which a node has. So there are n into k INV messages that are going to be sent, which is in fact a lot, given that there are only n nodes and n INV messages of them will be like the only usable ones. So it is a lot of wastage, because k minus 1 in n will be a huge number, considering that in scaling the Bitcoin network, we are trying to increase the k here. We are trying to increase the connectivity for various reasons. One of them is like trying to save us from eclipse attacks or other attacks that might happen. So this is the current problem right now, and with this, I'm gonna start. So this BIP introduces a new approach, a reconciliation-based approach. So what it tries to do is, instead of sending INV messages here, it uses flooding, but in a very sparse manner, and the transaction complexity now for storage, for bandwidth usage, is O of node n, which is a great reduction compared to what we had before. So the increasing the connectivity has saves us from partition attacks, which is here, and improving bandwidth transaction scaling, which allows us to improve the security of the network by increasing connectivity, which is in fact what we want. And on a high level, Erlay uses what we call as low fan out flooding. So this is a new concept which is introduced here, no fan out flooding. Plus, this introduces the reconciliation based approach. And first, let's go with what the low fan out flooding is. So generally, a Bitcoin transaction, a Bitcoin network has two types of connection: outgoing connections and the incoming connections. So outgoing connection currently has a limit of 8, and inbound connection has 125. And what it does is that the public nodes, which are very well connected, are supposed to send INV flooding messages, but only to the 8 outgoing connections that it has. There will be no flooding in the incoming connections. So this is what it tries to achieve. Only the well-connected network will be allowed to flood the transactions, and the other nodes or other networks will have to then get the transactions through the reconciliation-based approach. So it kind of like is this. The first layer is that the well-connected nodes get the transaction by flooding. Then the other nodes that are connected by them get it by the reconciliation-based approach. Now this introduces a problem, because flooding is a really fast process, and with that, only the well-connected nodes get to do it, and the private nodes and some not so well-connected public nodes are faced an issue that they are always behind in what the transactions the mempool will have. So let's say they get the transactions by flooding, and now I'll have to wait for the reconciliation-based transaction relay to share the data. Now the problem here is that the reconciliation-based approach has a limitation that it is only done 2 times per second, which is a huge problem right now, because there may be conditions when the network is very there is a lot of traffic on the network, and in this traffic, because of this limitation, the lower level nodes that are not that well connected and are gonna receive the transaction very late, or are gonna be late in the transaction that their mempool and may or may not be like a block behind. So this is what the problem is right now with Erlay protocol. Now
Right.
I would like,
So it's like in the
anyone-
specification itself that there will be like the period of reconciliation will be 2 times per second, right? Or it's just an implementation details that we can change.
I guess it is a implementation detail that is supposed to change after this. I guess when I was reading the paper, they said that they are just trying to assume like a normal traffic right now, and are like trying to implement the first version of Erlay. They are not considering the like extreme factors right now for like this to happen.
Do you
Right,
mean
makes sense.
2 times per second, or do you mean like 2 reconciliation rounds happen?
Like two reconciliation rounds per second. So it will reconcile with every peer every 2 seconds, every two times a second.
Oh,
2 times a second or every 2 seconds?
2 times per second.
Okay. Hey, Faisal has a question. Faisal, go ahead.
The question was on the same lines. Is it 2 times per second per node, or is it 1 times per second per node? So, like Prabhat, can you share your
Like,
source of?
There
yeah,
are.
sure.
I think the answer is in the BIP. So if we can pull up the BIP, we might able to figure it out.
Yes.
Yeah,
I
Prabhat,
think
go
the
ahead.
white paper mentions once. Yeah, please.
Yeah. So I guess there are 2 reconciliation rounds, and every round it reconciles with every of its peer. So this is what I like got from what I read.
I'm also trying to find it out in the BIP.
This was, I guess, discussed in another review of this, and that is where I got it from.
Okay. Yeah, I also remember reading it somewhere about the frequency, but can't seem to find it now. Strat, would you know?
No, like I'm not sure about the frequency at which it happens.
So okay, this one
It's in the PR description. It's in the PR description, and it's here. I'm sending it in the link chat here. And every 2 seconds, every node chooses a peer from its outbound connection in a predetermined order to reconcile with. Results in both sides learning the transaction known on the other side. So every 2 seconds, it will like choose one peer and reconcile with them. And yeah, so it seems like the frequency can be said in that way. It's like 1 reconciliation per 2 seconds.
Yeah, but in my opinion, it is currently too slow. Like,
I mean, yeah, that might cause problem because you are going node by node basis. Previously, we were going like flooding, so send it out to everybody in one go. Now we are going node by node basis, so each node will take some time, and then after 2 seconds, it will try the next one. I'm now thinking like, what if like the node is delayed in responding for more than 2 seconds? What it will do? Will it wait or will just go for the next one? But I guess like for that, we need to look into the code to see how it's working.
yeah,
If I remember right, it's also backward compatible. Like it also falls back. So if nothing
Right,
works,
yeah.
it sorts to the flooding mechanism. If
Right.
last case, the sort.
Yeah, there are 2 cases, like it sends a message. I guess there is a message that shows support for reconciliation, and then there is another message. Yeah, this one, send transaction reconciliation. So if this is sent and there is a positive response with the WTXID relay, because this like this protocol is based on the WTXIDs, so the node should send a positive response for this message and this message. Otherwise, it will fall back to the
Right.
non method.
Right. So this is strictly WTXID relay. So the node has to support WTXID relay as a service.
Yeah, it has to support it. Otherwise, it won't work. Because
Right.
this short keys that is introduced here, they are computed from WTXIDs. So if it doesn't support it, then it won't be able to create sketches, which is used
Right.
here for reconciliation.
Yeah.
Right.
Yeah.
There was another thing I remember we discussed in the review club. It was about compact block, and this is kind of like similar to Erlay. There were some references to Erlay there also. And compact block is this idea is like sending a sketch of a block, and from that sketch, the node's telling the other node what he is missing in its mempool, and then those transactions are sent to the node. I wonder like how it interacts with that. Is it similar, or it's gonna be the same also for block sending?
Yeah, from the algorithm itself, what you discussed is how the reconciliation happens. It like catches the symmetric difference from the sketch the other peer sends, and then sends back the like transactions. This like the node that has calculated is missing, and then also sends the transactions that the requested node was missing.
Right. Yeah. It's a very similar sketch-based approach, and I think it uses mini sketch also as a
Yeah.
backend for doing those sketches.
Yeah, it is based on mini sketch.
Right. So like we have like only a mini sketch library in C++, right? Kind of like those libsec-p packages, or there are like other mini sketch libraries in other language. Has anybody scoured for it?
Like there is one known as PinSketch, but like in which language it is implemented, I don't know that. Because inspiration of minisketch was from PinSketch.
Right. I'm trying to find out some details. Here's the Minisketch output page for people who want to dig deeper into Minisketch. And yes, lib Minisketch is the library. And yeah, it's C++. Very similar to how the libsec-p was done. Here's the GitHub. Cool. So what's cool in this protocol more? So this was like a nice brief understanding of like what the protocol is about. Anything you found more interesting in the implementation, how it was done?
Yeah, but what I found is that this protocol is a symmetric one. So there is a role-based like working here. So the first one that sends the first message, send transaction reconciliation message, is like a requester.
Right.
And like the other node is the responder. So what happens is that if first there is a send transaction reconciliation message, and whatever the response of the responder is, so let's say if it responds positively, then like it will send a request reconciliation message, and the request reconciliation message, it will send its sketch and a queue, which is the set difference it can accommodate
Right.
to extract. Sketch works in this way is that there are two special properties of sketch. Sketches basically is just like a way of encoding, like compressing the data we have and being able to extract the data from it effectively without like the loss of data. So there are first thing is that there is a upper limit on how much of data can be extracted from a sketch. So let's say if there is B bits of data per what we want to store, and there are C type of that can be stored. Only BC bits of data can be accommodated, and from these BC bits, these B bits of transactions or whatever we have, like short TXIDs, can be extracted. So if the size goes beyond this, we won't be able to extract the WTXID or the transactions from this. So one point is that. Second point is that it tries to calculate the symmetric distance, symmetric difference. So symmetric difference, what it wants to say is that suppose there are, this is the sketch 1 and this is the sketch 2. So what it will send is that this portion of data and this portion of data will be included in the symmetric sketch, and this won't be included because this is common to both of them.
Right.
The difference between both of them is that these transactions have only one owner, and this is like the transactions that both of these nodes will be interested in. So
Right.
I have an example. Let's say we have node 1, and node 1, let's say I'm referring as numerals the transaction. So let's say there is a transaction with 1, with 2, with 4, and with 6. Let's say these are the short TXIDs for now, and node 2 has 1, 2, 3, and 5. So what will happen is it will like create pad zeros here. So here I can add zeros to make it like same length, and then there is kind of like a XOR operation here. So if things are found in both of the blocks, then it will remain 0.
Right.
And this is also found in this. So both of them. So it remains 0. Now there is 3 missing in node 1, so it will be included in symmetric difference. 4 is also missing in 1, so it will be also included. 5 is missing and 6 is missing, so both of them will be missing, and this will constitute a symmetric difference.
Right.
So now what the node does is the responder is the one calculating this here. So now the responder has calculated this, and it will check from this. Let's say node 2 is the responder. It has checked that from the symmetric difference, transaction 3 and transaction 5 it has, and transaction 4 and transaction 6 it does not have. So
right.
what it will send is, it will like send a reconciled diff message. Reconciled diff message will send if the process was success, and will also send what transaction IDs, what short transaction IDs the node 2 is missing. So here it will send node 4, transaction 4 and 6, and after that what it will do is it will INV both transaction 3 and transaction 5. So the same protocol of INV get data and transaction is being done here again, but but here it is efficient because there is no repetition or no duplication being happening here.
Right.
So
but
now,
like, isn't it sounds like a bit redundant to send INV here? Because like at this point, the responder responded with the set difference, and with that, the requester can figure out what the responder doesn't have. So do the responder again needs to ask for those transactions via INV, or just the requester can send the transaction?
I guess it is to like comply with what the original procedure is. Like, I don't know why the INV is being sent. But the paper suggested was it wanted to like have the same procedure for sending the transaction, and they did not want to change it. The fact given that this transaction this node knows that the other node does not have these transactions. Even after that, the INV is being shared. Is there is a scenario where uh, the node stores a number of sketches in a for the node maintains a sketch per node for its peer, which it would have got if it would have
Did a simple INV thing.
did the
Right.
threading thing. So it maintains this thing. So let's suppose it has this transaction 3 in one of these and not here where the reconciliation was happening. So I think it's for that scenario. Otherwise I don't think it should be here, and it can be discussed can be a
So,
discussion.
like the BIP includes the intended protocol flow. I have sent the link in the chat, and there we can see the diagram. And in that diagram, it sends after the requester sends the reconciliation difference, then it sends an inventory message to Bob, and Bob sends an inventory message to Alice. And with that, then the usual workflow happens of responding to inventory with get data, and then the transaction actually floods. Yes, Faisal, go ahead.
Hey, Prabhat, can you go back to your notepad? I had a question.
Yeah, sure.
Can you just scroll up a little bit further? Yeah, okay, yeah, perfect. A little bit, yeah. Okay, so yeah, what I understand is that transactions 4 and 6 were with node 1, right? Which node 1 is the initiator, right, of this reconciliation process.
Yeah.
Right? And 4 and 6 are with node 1 and they are not with node 2, okay? So now what node 2 is doing is node 3 gets informed about transaction 3 and transaction 5, but node 2 already has 4 and 6, correct?
Right, yes.
Yeah, okay. So can you scroll down a little? Yeah, so after this reconciliation, node 2, from what I understand, sends a success message to node 1, right? And it also sends transactions 4 and 6, right? Now this transaction 4 and 6 were already with node 1. So what is the wisdom behind sending these transactions to node 1?
Yeah,
no, I don't think they do that. They send a set difference, and that is the success, right? If the difference is calculatable.
Yeah, no, the thing is that the node 2 is the one doing the calculations here, and it only sends the transactions it wants the other node wants to have. So in the BIP it is clearly written, but it sends the data it sends. So yeah, ask short here is the short here is that the sender did not have this being sent here. It is because the node 2 also want to have the transaction data from node 1.
Right. That they are sending via inventory, basically.
Yeah.
Yeah. I think what was confusing in the notebook, can we go back again in the notebook?
Yeah.
Yeah, here, so node 2 already knows that node 1 has 4 and 6 that it doesn't have. So it's gonna send an inventory for 4 and 6, saying hey, it's gonna send an inventory for 3 and 5, and node 1 from the sketch difference can figure out that node 2 does not have 4 and 6. So it will send an inventory of 4 and 6 to node 2.
Yeah.
Is that right?
Yeah, it will send the node 1 will send the inventory of 4 and 6, and then the same procedure of inventory, get data and transaction will happen.
Right. So they are basically sending each other the symmetric opposite of what the other person does not have, and they can figure that out from the set difference that the node 2 sent to node 1.
Yeah, but the problem here is that only node 2 knows what the set difference is. Node 1 does not have the set difference by the time.
But they tell the set difference, right?
Yeah, but the set difference is being sent here.
Yeah, so if success equals to true, that is success is set if the difference could be found. So if the difference is not found, then success is false, and then we fall back to the previous mechanism of like just sending inventory data.
Yeah, so there is a case here that if the success is not true for the first case, so the first procedure is that a sketch message is being sent by, so the what the like workflow is, there will be a send like transaction reconciliation, then there will be a request return, and then there will be the node 1 will be sending the sketch of it. So if the like the node 2 sends a success of false, then it like request a extended sketch with the higher capacity to like extract the data from. There is another message like here in the BIP. Yeah, this one. So for the first false, the extended sketch is being demanded from node 1, and if this one also fails, then the method fallbacks to but the usual pattern.
Right. Yeah. I think the diagram above, there is a diagram that like explains it pretty clearly. If you scroll up, yes, this one. So Alice is requesting for consolation, and Bob sends back a sketch, and Alice tries to find a difference. If he found the difference, then he knows what Bob is missing, right? And then Alice sends a reconciliation difference to Bob, and with that, Bob knows that what Alice is missing, and then they do in with each other. And in the case when the first success is false, then Alice sends a request sketch transaction extension, request a sketch extension, and tries again. Now I'm wondering like how many times it tries until it gives up.
Like the number of tries is not like clearly defined in the paper, I guess. There are only 2 tries.
Feels like it will be an implementation detail and it will be visible in the code only.
Yeah.
But correctly, they try this extension, and if that extension also doesn't work, they fall back to the normal mechanism.
Okay. So they try just one extension, and if it doesn't work, fall back.
Yeah, ideally it should work ideally it should succeed.
Mm-hmm.
Yeah,
right.
I'm also like appreciating the fact right now that it's only done for outbound connections, because like here Alice does an outbound connection to Bob. Imagine if Bob lies about the difference,
right,
and sends back the wrong difference to Alice. So Bob would have to. So like Bob wouldn't have to. If Bob can lie, it doesn't have to bear any cost, because it doesn't have to bear any cost if Bob lies. Like you can just make up whatever you want. Like I can say I'm missing I can spit out any transaction, right? So because it's done to outbound connections, it means like we control who our peers are. So so it's kind of like as long as we maintain peer diversity and select good outbound peers to connect to, the chance of actually connecting to a liar Bob is much less.
Right. It can happen more if we allow it for inbound, because other people can connect to us and they can eclipse us in that way.
Yeah, they could, if it was an inbound connection, they could just lie to us and tell whatever set difference they want.
Right. This was an interesting point, that it's only done for outbound.
Yeah.
Right. Makes sense. Okay, cool. I guess like this was a good summary of the protocol. Maybe we want to go over the questions now that was listed in the issue, and maybe we can open it up to the community and people try to answer them, and that can ask for some discussion.
Yeah, sure. So like the first question is that what is bandwidth, and why is this new protocol important. So anybody wanna give a try?
Yeah, we kind of like summarize it already, but anybody want to give a quick try? Yeah, Faisal.
Okay. So bandwidth in the context that we are discussing is the amount of information that can be transmitted over the Bitcoin network in a given amount of time. And correct me if midway if I'm wrong. I'm assuming I'm correct, so I'll proceed. Why is this new protocol important? Why is this new protocol important? As per like my understanding, almost 50% of the bandwidth that a node runner spends is on a transaction relay. And for Bitcoin, a decentralized network like Bitcoin, for it to be robust, it's highly important that a peer ensures good network connectivity. And more the number of peers that you connect with, the more the bandwidth you eat up, because in the contemporary mechanism, you have to share announcement message with all your inbound and outbound peers, and you want to be connected with as many people as possible to ensure that you're connected with a diversified set of people. So as in when your connectivity scales in the network, your bandwidth usage exponentially increases, and you don't want that to happen, because when the bandwidth increases, it filters out the number of people that can run a node. And that is why this protocol I feel is very important, because it can help the Bitcoin network scale without putting a lot of burden of bearing the bandwidth on the node runners.
Awesome. Thanks for that amazing summary. Yes, that's exactly what we are up to here. And bandwidth is one of the scarce resource right now, kind of like more scarce than compute, because in certain parts of the world, bandwidth is quite costly. And so reducing the bandwidth for node runners is always good for decentralization.
Cool. Also shared to an RPC, which can be used to measure bandwidth for each message type you send. It's still a draft PR. It's like I do want to test this PR, so I would use this RPC, cherry pick it on top, and measure the bandwidth for the message type.
Right. Currently, we get only the call counts, like how many messages were sent of each type, not the total data.
I think they also do get the bytes somewhere, but not for every single message. People doing the monitoring, they actually use trace points to extract those data. But that requires more like setting it up and like more knowledge about how trace points work. So this RPC is very simple, even for developers. You just need to run the RPC call and you'll get the exact stats for every single message type.
Right. Yeah, that will be really useful for like CBF node runners, because they always get like heavy bandwidth load on them.
CBF?
That's completely non-contextual here, like compact block filters, like people who are serving compact block filters. And they get a lot of like bandwidth load on them. Usually it's off by default, but if you turn that on, you'll get a lot of bandwidth. Okay, cool. Let's move on to the next one.
Okay, then the other question is, what exactly is Erlay and is it backward compatible? So this has already been answered. So what are short transaction IDs? We can look in the BIP. This is the new format of storing the transaction IDs in this caches in a more compact way. Currently, a TXID is 32 bytes and this is 32 bits. So there is a lot of being saved here. And this actually uses two new hashes, a tagged hash, which is in BIP 340, and zip hash, which is in BIP 141. So, and there is use of sort here. The use of sort here is that because we are reducing the size of short IDs a lot, there can be a scenario where the attacker can grind the transaction. So to introduce randomness, sort 1 and sort 2 are added here, and sort 1 is added from sort 1 and sort 2 are both added from both of the peers. So there can be utilization of one sort, but if both of the peers are participating in like securing the transaction, it is better. And what the tag hash does is this
Right.
creates a like hatch, which is another variable from this tag hash. The first 8 bytes are used in K0, second 8 bytes are used in K1, and then it calculates the short TXID. But there is a 1 being added here. This is because from what I learned is that short TXIDs only work in non-zero range, so it has to be greater than 1, and also has to be like less than this big value here.
Right. Makes sense. So it's kind of like evenly distributed within that range, 1 to all the Fs.
Yeah.
Right.
That is it.
Yeah, that's a cool concept. And tagged hash are like a nice concept. It's very simple, so people interested for that can look into BIP 340. It was introduced with Taproot.
Yeah. So the another question is that the reconciliation scheme is asymmetric. If we have an output here, we initiate the reconciliation, and why not a symmetric design? So anybody wanna give it a shot?
Yep, Faisal.
Okay, what I understand from asymmetric in this context is that this process can be initiated. Like you can only initiate this process with your outbound peers, not with your inbound peers. So currently, the flooding mechanism that is used in Bitcoin is symmetric because you can share or announce messages to both your outbound peers and your inbound peers. What's different in Erlay is that you only share these messages with your outbound peers. That's what is being referred to as asymmetric. Now, why is it asymmetric? Why do we only do this with outbound peers? Again, to reduce a bandwidth. Because if we are sharing these messages or announcing these messages with inbound peers, then there's no concept in having Erlay. What I understand is that Erlay gets the best of both worlds in a distributed system. Ideally, some distributed systems use flooding, like Bitcoin does, and some use only reconciliation. The issue with flooding is that the latency is less, but the bandwidth usurped is a lot. And the issue with only reconciliation is that the bandwidth consumed is very little, but the latency is very high. What Erlay does is that it gives the best of both the worlds. So you only what you do is you only indulge in fan out flooding with your outbound peers, okay? And when there's a need of reconciliation, you do reconciliation, and you only do it with your outbound peers to ensure that the messages are not repeated, and you're not sending redundant messages to peers that already have that information, and thereby when you scale the network, the bandwidth does not scale in a linear manner. That's my understanding.
Right. Yeah, I mean, like, there's another asymmetry is like there is always a requester and responder, and you never change the role from being a requester to being a responder with your peer. So if Alice connects with Bob, then Alice is always the requester and Bob is the responder, right? And yeah, and as Strat said, like another problem of doing it with other way around is like Bob connects to Alex and Bob becomes the requester and Alice be the responder for inbound connection. It can like cause this kind of like eclipse attacks, right? So we can like have like inbounds who are like connected to us strategically and sending us like garbage sketches.
Yeah, but there is a like problem I had with this design. Like if I consider the case of private nodes which only has outgoing connections, so the responder has to do the calculation for like symmetric design. So I'm also like leaving the fact that only the responder will have to calculate and all have to do the computation, and I only get like the reward of what it has done. I'm not the one here doing any extra work just because I am sending the like first message of initiating this early transaction. Really.
Right. But that's also like okay, right? Because in that case, like from Bob's perspective, Alice is an inbound connection, and we are only calculating sketches for inbound connections because we are only responder to people who are requesting, and request is done to outbound. So from responder's perspective, it's an inbound connection. So then the inbound number maximum is 7. So we will only have 7 nodes asking us for sketches. Is that right?
Yeah, that's right.
Right. And then we'll.
I think
Yeah, go
Raju
ahead.
said you'll only have. I mean, you'll only have 7 inbound peers is what I heard. That shouldn't be the case, right? You can have more than 7 inbound peers, because if you can have more than 7 inbound connections with private nodes who can reach out to you to reconcile, right?
Like you can add private nodes, but can you? I don't know if you can tell other people to connect with you. You can connect with other people, but can you tell other nodes to connect with you? I don't think so. And
No, I mean, yeah. For instance, if I am a node, okay, and I have inbound connections, right? I can have, let's say, 100 inbound connections with private nodes, right? They are the ones who have initiated a connection with me, okay, and let's say they're all private nodes, and all of them want to reconcile with me.
No, you can't. Like the inbound max cap is 7.
That's the outbound max cap, is it, or the inbound max cap?
No. Outbound is 125. Inbound is 7.
No, it's the opposite.
No, Raj.
Oh, it's the opposite. Oh, okay.
Yes.
Sorry. I'm wrong. Okay. Oh, okay. So outbound is 7, inbound is 125, right? Oh, man. I was like thinking completely opposite. Then yeah, everything I said is wrong.
Outbound is 8.
It's just the opposite, yeah.
Yeah. Then you have like all 125 people asking you for
Reconciliation.
Yeah.
So we hope that the cost here to do the reconciliation, it is less than the flooding. Like there's a cost to pay in the bandwidth usage. So we are like, if you use this mechanism, we are kind of saying that we are willing to pay this compute cost to compute the sketches, and that's better for us than the excessive bandwidth usage happening. It's like a 50% reduction in bandwidth or something. Like I don't remember the exact stats.
I think it's 44% bandwidth reduction and 2.6% latency increase. Like it increases the latency by 2.6%, which is negligible, but it reduces the bandwidth by 44%, which is like an exponential upgrade.
Right. Okay.
Then we can move to the next question.
Yep.
Then the next question is, the private nodes almost always lag behind in the mempool because private nodes don't have incoming connections. So only they can do is reconcile with the public nodes. That introduces a lot of like delay in them getting any transactions which in the early era of the Bitcoin we are getting. So like, isn't this a big problem? Then the private with this then the frequency of reconciliation, the private nodes would like to have like a higher frequency compared to what the public nodes have, and then they will also like to have more requests from its incoming outgoing connections. Then this would like create a lot of pressure on the public nodes that are well connected, that do the flooding, because they are the ones in the end that will be like the responder for most of the reconciliations. So that is big issue that is being created.
Right, and like this latency is like becomes a bit problematic for the private nodes.
Yeah, but it sure gives like protection from eclipse attacks and like partition attacks. But like this is a like huge disadvantage that this protocol.
So my theory would be like why like private nodes use mempool. Like what would be the main purpose for which private nodes use mempool? So I think if we can figure that out, we could get the answer.
That's a good way of like asking it. And generally, like people who are running private node, they are not worried about mempool in the first place for the application that you are using the private node for.
Yeah. Like as long as like my theory would be that as long as like the miners, they want public nodes, like they are the ones who get all the transactions into the block. So even if the mempool for a private node is lagging, it's okay, because ultimately the private nodes want the blocks from the miners. Like it will get the transactions via that.
Right.
It doesn't really participate in relay other than its own transaction relay.
Right. Yeah.
Would be
I mean, that makes sense. The fact that a node is trying to be private, that means like he doesn't want to be part of the gossip. And that by definition means like he will lag on mempool.
yeah.
Yeah, so like it's okay for them to lag because of them being like not participating in the network.
Yeah. They mostly, like in those cases, at least I have seen, like people will run private node when they are like doing a private RPC service or something, or like wants to get their client transaction directly to a miner's mempool or something. Like it's kind of like a proxy node between the network, not a fully contributing P2P node. Okay,
Yeah.
cool. That was good. That was good discussion. Let's move ahead.
Yeah, okay. Then with the introduction of Erlay, nodes need to store extra data in form of sketches and needs to support its operation. Like now the nodes have a problem that the sketches can be huge and the number of connections is gonna increase as we scale the network. So it will be a huge like burden on the node to store this much of sketches and also update it. Also now that it has to like, support its operation. So like, is this a favorable change that we are like trying to introduce in favor of saving the bandwidth?
Right. I mean, like the answer could be again traced back to that point of like, what is the trade-off here? Like, how much is the cost in computation and storage against the cost of savings in bandwidth? And from the number, it seems like it's just 40% bandwidth reduction. That's cost gonna be always higher than just storing few sketches. Yeah. So like, the sketch can, in theory, never be larger than a it can be larger than a block because mempool can grow up to like 300, 500 MB or something, and the sketch will be kind of like representation of the mempool. So for each node, if we are talking about say 130 connections, we are kind of like talking around few GB of data, like 1 GB of data. Yeah, somebody can do the napkin math for me. 130 times 300 MB in average, but probably sketches will be shorter than that.
So like I guess what I heard is what I saw is that sketches after every for a node to node connection, sketches from both sides are discarded after the reconciliations, and there is a new sketch form after every like reconciliation. So it is not gonna like scale to like mempool size level. It is gonna remain shorter.
Yeah, definitely much shorter, and it's kind of like updated real time as people are reconciling with each other. Every reconciliation is like wipes off the data and you start from zero.
Yeah.
So I guess like that's cool for like 40% bandwidth reduction. Faisal has a question. Faisal, go ahead.
You store a sketch for each one of your outbound peer only, right? So there's 300 MB into 8 maximum, not 300 MB into 100 or 120 or 130, right?
Yeah.
I think you will do that for the inbound also, no?
No.
Oh yeah.
Yeah, we have to do that for the inbound too.
Because
like,
the inbound will gonna ask us for the sketch.
Oh, okay.
Oh, no,
okay.
like
In that case, you're the responder, not the initiator.
Yeah.
Yeah.
So both of the times, if I'm the responder and if I'm the initiator, both of the times I'll have to like have a sketch for the connection.
Right. Thanks. Yeah.
Yeah. Okay, so that is it. And
That's a good question. And it should be like nice to in the peer review, like to collect data and like review it in the PR, like tell them what's the extra data. Like it's an interesting statistic to tell everyone. I like the question.
Right. It's a good question.
Yeah. We can move on.
Awesome.
Yeah. Yes. Yeah. Okay. So the next question is, why is the reconciliation-based approach scales better? Then I guess it has been answered. Now the next question is, frequency of reconciliation is fixed at 1 every 2 seconds, and why fixed and not dynamic? So like, anybody has any thoughts? Why is it not dynamic? Like, what I heard from the devs is that if after every reconciliation I'm trying to change the frequency, then it will be a huge burden for the node, kind of, and it is like then becomes prone to a lot of attacks, because if there is not much traffic, then the frequency of reconciliation will be less, and like the effectiveness will be decreased of having reconciliation. Anybody wanna add up to this?
Yeah, like we use dynamic like timing, then sending transactions right now, mostly to protect against inbound connections, because inbound connections could be attackers. So we don't want to be we don't want us to be able to be fingerprinted. So that's the main purpose for a dynamic timing delays. In Erlay, since we are only sending it to outbound connections, like it's just more overhead. We don't really need it. And even if we did dynamic, it would be like better to do it less than 2 seconds. I don't think that really adds much value.
Also, like it could be potentially detriment for lagging, like the latency can go higher if the traffic is low, as the node is like reconciling less frequently. And then suddenly if the traffic jumps up, it's gonna take all the nodes to dynamically adjust for it. And that's gonna increase lagging also.
Makes sense. More overhead.
Yeah. But another question could be like, where did this 2 seconds come from? Like, why not 1 second? But that could be like some kind of like benchmarking. Usually like the way it's done is like some estimation done by the dev and coming up with a good enough number. So it could be 3, it could be 1 or 1.5, 3.5, but 2 is kind of like optimum balance.
Yes, I'm just shooting in the dark, but I mean outbound tier, I mean private nodes. Okay, if we're talking about private nodes in this situation, the only mechanism for them is reconciliation. They're not a part of the flooding environment. Okay, so and private nodes, like they only if a private node announces a transaction for which state is a source, and simultaneously it also initiates the reconciliation process, could it be like an attack vector to figure out the source of the origin of that transaction, even though it's private, because it's announced a transaction at a certain point in time, and immediately it initiates a reconciliation process, and that is why we need a lag of at least 2 seconds to camouflage the fact that that private node is the source of a transaction when it is reconciling?
That's a good question. My hunch is like the private node kind of like by because it sends this transaction, and he's the first transaction in the network, and it does not participate in flooding. So the node it's connected to, by that definition, the node always knows that this transaction originated from this private node. I might be wrong, but seems like you're always prone to that attack vector, just because of the fact that you are private and you just announced your transaction to one single guy, and that single guy knows that it's you because nobody else tells about that transaction.
Right. Okay. All right. Yeah. Thanks.
I mean, this is a good question because this is a problem right now also in the network, because like if you broadcast a transaction, it's kind of like normal for other people to know that this is where the transaction first originated in. And if an attacker wants to probe transaction, what they would do is like they would try to capture as much as your P2P connections as possible, and then it can basically see all your wallet related transactions. So yeah, so for that privacy reason, it's probably much better approach for wallet apps to connect to various like broadcast providers, right? There are so many broadcast providers out there which provide service for their free, even if they don't have their full node. And even if they have their full node, they usually better off keeping it public. And I think there are some mechanisms for like camouflaging that also in the P2P protocol.
Okay, thanks.
Yeah, that was a good one.
Yeah.
Okay, cool. And then the last one is about the analysis of the effectiveness of protocol, which is basically this whole 1 hour session was all about.
Yeah.
Yes. So
Yeah,
cool. So we're on our time. Yeah, this was a really nice, fun chat. Thanks, Prabhat, for preparing it up for us.
This is awesome. Thank you. I enjoyed it.
Yes, I learned a lot. And this was good. Maybe like for next one, but maybe like for next one, we can attempt for the PR. I saw the PR. It's kind of like 2,000 lines of code. Gonna be pretty hectic to review.
That's the draft one, which contains the entire thing. Like
okay,
there's one PR to review right now, but even that is many commits. Like I think it's 28765. I'm checking how many commits are. Oh, it's 6 commits. So maybe we could like just review 3 commits in the next week, and then the next 3 commits later.
Yeah, that makes sense. Is it like the draft PR you're talking about, the first 3 commits of the draft PR?
No, I'll just share the link in the chat.
Yeah. Okay. That helps. Failed reconciliation set. Okay. So this is 28675, and so this is about like the reconciliation set mechanism and the P2P part of it, right? Yeah, this is like seems like more manageable to review, and it'll be fun to review actually, like after this theory.
Yeah, definitely.
Definitely, we can attempt this in the next one.
Should we do all 6 commits or just 3 commits? And I'm wondering which is easy.
I guess like that's up to the host, but my safe assumption will be the first 3 commits. It's gonna be heavy. My hunch is it's gonna be heavy.
Yeah, it's better to understand better the first 3.
Yeah. It's always better to take time with these things and let all the concepts sink in. That's where like it's become more fun. Yeah, so first 3 commits, definitely, yep. We can schedule that for the next one. Any other feedback from other guys? Last round of questions.
Just some closing comments. Firstly, I'd like to thank Prabhat. I think the session was awesome, and he explained a lot of very difficult concepts in a very easy to understand manner in the notepad. So like, the session was absolutely worthwhile, and congratulations for that. And yeah, I'd like to thank Status and Raj as usual, and thanks everyone for showing up.
Awesome. Thanks for the nice word, and thanks for the amazing work, Prabhat.
Yeah, thank you, Faisal, for coming.
Yes. This is always fun. I joined after a long time, and like, I remember how fun it was. Thanks for doing this, and thanks everybody for showing up. Yeah, I'll try to be more consistent here from now on.
Awesome.
Cool. Okay, cool. So let's call it a day. This was a nice conversation. So this is a wrap. Thanks everybody for joining up. We do this every second Thursday in Bitshala Discord. Check the description below for all the links, and follow us on Twitter and Discord for all our updates. Thank you everybody. Bye-bye. Have a good day. Good night wherever you are.
Good night.